Hello everyone. This is to supplement the lesson that we're going to study today. We are starting inverse functions, and this is a kind of a function of a function. We have been studying those, right? So if we have a function f of x, we could use the output of it and put it into a different function, right? So we can say some kind of a g of f of x. So we'll take y and put it in there. We want to find out if there is an easy way to understand a function that returns us back to the original value, back to the x. I hope you can see what I'm writing. I'm going to do it bigger. So here is what we are trying to do. We're trying to find a function. Here is our x and y, for example. These are x and y axes, okay? So I'm going to mark them now, and right away I'm going to erase them because I want to reuse the letters and I don't want it to be confusing. So I have some function. I don't know what it is. I know what it is, but it's any function, right? I want to try to find a function that returns me to x. What does it mean to return me to x? So this is my f of x, right? Every point on it, if I take any point on it, right, for example here, it has two coordinates. One of them is x. This is an actual number x, right? That's why I erased the name of the axis. And the y coordinate of it is y, which is f of x. Alright, so every point on this curve is has two coordinates, of which one is x, the second one is f of x, right? X, y, basically. I like to now put the output of this function into this g, right? I take the output of this function, I bring it back to this x-axis so that it can be an input again, right? So this value right here on the number line is f of x. I've taken my f of x from the y-axis and I've brought it over to the x-axis. There is a symmetry here, right? I'm moving it along this line that's at 45 degrees. This triangle here has sides that are same, right? This side is equal to this side. A triangle that has two equal sides has 45 degrees at the base. Alright, I take this f of x, bring it back to the x-axis. What I want to get from it is x, right? So I want some function into which when I put the f of x in, I get x out. I get x on the y-axis. So what is it? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'd like to get this number out of my function. So when I put it in, I want to get this number. So this is a point on my new function g of x now, right? Well, what can I say about it? I have this triangle that has equal sides. I have another shape here that has equal sides because I wanted to get the x out, so necessarily this whole side here equals this whole side here, right? So there is a complete symmetry between this rectangle, for example, and this rectangle, right? They're the same sides, right? The shorter and the longer are the x and f of x. Let's look at this point. What are its coordinates? Its x coordinate is actually f of x. Its y coordinate is x because that's what I wanted, right? So I made a point on my function that I'm looking for from the point on the function that I had. In order to make it, I put the result of my original function in as an input, and I told it that I want the output to be equal to my input to f of x, right? What I got is a symmetric shape that has same sides everywhere. Because of the symmetry, I now know what I'm getting, right? I'm getting a point whose coordinates are basically swapped. I started with a point whose coordinates are x and f of x. I ended with a point whose coordinates are f of x and x. What happened is x and y got swapped. I know two things about such functions, right? We've studied them before. When you swap x and y, what happens is your axis gets swapped, right? You basically reflect the picture, the graph of a function, which is a picture, about the diagonal y equals x, right? Because one point on the function is symmetric about the diagonal, it means every point is going to be symmetric, because I didn't pick any special point, I picked a random point, right? So I'm going to get something that is symmetric, and I'm going to do my best to draw it as a symmetric function. It's going to be something like this. Alright, so this is my g of x. So I learned two things. G of x is symmetric if, rewind, I was looking for a function that brings me back from f of x back to the x. I learned how to make it by just doing what I wanted it to do, right? I said I wanted to bring it back to x. I made a function that brings me back to x. I know that it's symmetric about the diagonal, and I know that for every point x and y are swapped. If for every point x and y are swapped, then I can take any function that I have written down. For example, f of x, let's take one that's, I don't know, 2x. Now I know that the inverse function is such, so 2x equals y. When I swap x and y, I'm going to get it, right? So the inverse g of x is 2y equals x, right? And then I can work to figure out what is it as y as a function of x, right? Y equals x over 2. So y equals x over 2 is actually my inverse function. Does it work? 2x and x over 2. I can try and draw them. 2x is aligned with the slope of 2. X over 2 is aligned with the slope of 1/2. When you draw functions for 40 years, you become really good at drawing pretty lines. Look at that, they're symmetric actually. This is my line of symmetry. Everything worked out. I can take a very crazy function that, for example, y equals, let me try something else first, 5x squared. I want an inverse function, so I swap y's and x's, so x equals 5y squared. What does it mean for y? So y squared equals x divided by 5. Y, now I just solved the equation for y, right? Y equals square root of everything on the right, x over 5. Could be plus minus, and now I'm really in trouble. First of all, I'm going to grab the 1 over square root of 5 as a number, as a constant, and I have square root of x left here. Well, let's draw it. My original function is 5x squared. I know that what it is an x squared that's stretched up by a factor of 5. Let me, well, in any case, the problem is that it exists on both sides of my graph. When a function exists on both sides, when I reflect it, it's going to exist on both sides of the x-axis. So it becomes quite a nasty function. See, here's my square root of x, the positive part of it. Here's the negative part of it, the minus square root of x. I don't like it because I don't like functions which have dual outputs, right? I put my x in, I get two results out of it, right? Here and here. So normally when we try to get an inverse function, we limit the we'll limit one of them so that the domain and range don't get this duality, right? So we'd take x only positive for 5x squared, and then we'd get an inverse for it, and it's going to be 1 over square root of 5 square root of x, and then we don't have to do the funny plus minus here. Alright? Sometimes you cannot write things down exactly the way we like things written down. For example, what if our original function y is, say, 2x squared plus 3x minus 7. What is the inverse of it? And we're going to define it for only positive x's. For example, the inverse function, we usually mark it of minus 1, is our question. So let's swap all x's and y's. X equals 2y squared plus 3y minus 7. Now we'd like to figure out what is the y. Sometimes we cannot, right? Sometimes this is the best we can actually do. We don't have an expression here for y equals something. We cannot actually grab the y out of it. Sometimes we're more lucky. For example, y equals x squared, let's say plus 4x plus 4. This is a full square, right? It becomes x plus 2 squared. When we get the inverse function, we change x's and y's, so x is y plus 2 squared. Because it's so nice, we can actually figure out our stuff, right? We can take a square root on both sides, and then we subtract 2, so we get y equals square root of x minus 2. This time we lucked out, right? Because we can actually get an expression that we can tolerate, that we can digest. Sometimes the original function is such that when you swap y's and x's, you get something that cannot be solved in terms of y on the left side. But you can at least write it down, right? So this understanding here, let's go back. We wanted a function that brings us back to our x from some function, right? We figured out how to get one point. For this one point, we find out that it's symmetric as a picture, and its coordinates are swapped as an algebraic expression, right? From swapping of coordinates, we realize that for any function that can be written down, the inverse can be written down from it by swapping x and y. And that concludes this introduction. So I hope that it takes a little time to digest, and we are hopefully going to get back to it. But this is the true power of algebra, right? Even for functions that we don't know of. I started with a picture with a random line. This could be something from an experiment, right? That as time goes by, the number of infected people grows as this curve, and I want the inverse function. I don't know why would you want an inverse function of that, but it could be some random data, right? Some points that I've taken as an experiment. So I don't know what the function is, but I know how to make an inverse one. Just reflect it and you have it. Alright, I'll see you all tonight at 6 o'clock.